How about now? There we go. Okay, so we're going to talk about token engineering in practice. I'm going to basically start by reiterating a little bit of what we've talked about before, which is that these are in fact complex systems, and we're going to work our way down from the concept of systems. Their sort of general system theory helps us understand the way that things work in the world, regardless of what the sort of medium is. We're moving into complex systems because these things are sort of greater than the sum of their parts, and in fact social systems are complex, economic systems are a subset of social systems, and now we're talking about these blockchain enabled economic systems, which when sort of modeled formally tend to be dynamic, networked, adaptive, multi-scale systems. And with this sort of understanding, we can think about what kinds of tools and methods and approaches might apply. For time, I won't sort of go into the details of how to map Bitcoin into this sort of set of abstract sort of properties, but there'll be a paper about that at some point by one of the actual speakers who's later this afternoon, Chris Peruk. We want to talk about the relationship between economic systems and token systems, token economies. For starters, the economic systems are the things that we really care about, right? We might be engineering tokens, but the tokens are just sort of this now tangible economic component. It's a representation of a thing or a right, or could be a good, could be a service, it could be functionally a currency, but at the end of the day, we actually engineer them in order to drive a certain behavior in the economic system as a whole, which is actually a level of abstraction above the software itself. And I try to make this point pretty closely because often, when I first get involved with a project, I get handed a protocol specification. And I'm like, cool, that's the plant of the system, it's the machinery, this is what someone can do, but like, what will they do? What sort of happens? What's the extra layers of incentive control embedded through the tokens? Yeah, we don't really know. Well, what are we trying to accomplish? High-level business goals. We kind of work our way down from a representation of the economic system of interest down to what elements are sort of still under our control to design, what elements are in fact sort of predetermined by the use case or the software, etc. And ultimately, we want to design generally steering systems. And if people were around for Web3, I talked a lot about cybernetics and the sort of history of steering systems and what it means to design them. Here we're going to move on and stick to the sort of engineering aspects. So engineering's sort of critical bedfellow is science, and science helps us understand the things that we observe, to understand things that might happen in the future. And we really think about this in terms of three kinds of science. We have analytical science, which is basically mathematics, but it's applied mathematics to systems we care about. We represent those systems, and in a sense, when you write down a mathematical model of a system, you're saying, here's an analogy, here's a story, but that story actually tells you something back. So unlike a sort of written language story, when you say, suppose the world works like this in mathematics, you can use sort of manipulations, theorems, proofs to say, wow, if the world worked like that, then this other thing must be true. So we sort of have formal assumptions in, formal conclusions out, but not necessarily guarantees that that's how the real world works. We can sort of power up these sort of storytelling exercises with these computational models. They're a bit like, guess you could think about them as thought experiments just supercharged. So we're still just saying, suppose the world works like this, and up to the degree those assumptions end up being true, the conclusions that you might reach from looking at those analyses might be true. But with the degree of computing power we have now, we can run really wide array of these thought experiments and actually make inferences not just about what will happen, but how sensitive the outcomes are to the assumptions that we made in the first place. And of course, we have our empirical studies, which are always critical. Backtest your models, understand how they work. But often we can't do empirical until we're further along. And so the analytical and computational are the things that help us understand that which does not exist yet, or that which we wish to instantiate. So in the engineering side of this, we have this concept of sort of design and development, of verification and validation. And while I won't sort of work all the way through this, the big picture here is that in the engineering world, where you're building composed complex systems, you've got parts interacting with each other, experts over the subsystems, composed into wholes, you have to do this thing where you design something and you define formally its abstraction, then you have to worry about how to instantiate instantiate it. This might sound weird, but it's like blueprints for a building and then building a building. If you have to get to something that has a necessary set of different expertises, you need this engineering practice where you design at the level of abstraction, and then the components or subsystems have properties that are necessarily true, at least sort of up to whatever the sort of tolerances are in those systems. And then the systems below are then built to meet those specifications and tested against them. And so we talk about this in terms of validation and verification pretty much in every engineering class ever. We start with some system level goals, we design for them, and we work our way down to the lower level systems. So high level blueprints for your building might become sort of specific requirements for a set of stairwells, or maybe for even the plumbing or the electrical systems, etc. And then the experts in those domains have designs at their level, and that might have subsystems. And eventually, somewhere along the line, someone's laying bricks and laying pipes, etc. And this is how we actually realize large-scale systems with heterogeneous elements. And in the case of crypto systems, we have this really important problem. We don't actually know what's going to happen. So there's this emergence chasm in my drawing, which basically says, well, we actually are designing for the emergent behavior of a bunch of actors we don't actually control. It's not quite the same as designing a building after all. It's actually a little closer to things like our power grids and our road systems. If you think about a road system, you actually are only laying down what people can do. The traffic patterns that emerge are not under your control. And in fact, you may very well build a perfectly reasonable intersection that has tons of accidents in it. And you might not even know why, but then you probably should redesign, or you might need an anti-pattern, like we discussed in the previous talk, to say, wait, like, why did there happen to be lots of accidents here? There was nothing wrong with the road from a sort of first principles of roads perspective. And so we actually bring in this sort of idea of the infrastructure, the engineered thing, only sort of allowing people to do things, and then the actual implemented thing is including emergent behavior over the thing constructed. And that's really tricky, but we're going to talk a little bit about how we go about dealing with it. And it starts with working through processes like saying, what do I really want to accomplish at a high level? And even though I can't strictly guarantee it, I want to keep in mind, and I want to work backwards from it before I start constructing something that I hope to achieve those properties. So from a simulation testing perspective, we break the world up into two pretty important elements. One is how the world works, and the other is what people do about it. And we can approach this from the whole sort of life cycle of the design process, where early on we might have these stochastic differential equations as the state update of the system. Some noisy processes might be out of our control, but at least up to a degree, if you do something, the consequence of those actions is reasonably deterministic. It's just that the behavior is not. And so you need population level agent models or agent-based models. And sort of as you move to the right on this, you're basically diving into finer and finer detail. And after you are building software, it generally makes sense to run backtests even between your models and your designs and the software you've implemented itself. So if you said in my design and in my, say, Python code, when the following behaviors are exhibited, the system does this. If I go to my chain code and I run agents that are emulated and I don't get the same behaviors, well then either my model wasn't very good or my code is wrong. And I can sort of begin to say, let's find this and fix this before we go into a production system. And in fact, after this, we can use the same modeling paradigms to analyze or understand the observed behavior on a live net. In general, we work with this sort of abstracted version of a decision problem. Pretty simply put, this diamond is people making decisions outside of our control. It can be many people, it can be many different kinds of people, it can be a whole mess of complicated things, but what matters is that their decisions are based on their private signals, their private beliefs, and we don't know what they are. So we don't want to say that they're rational in the sense that they behave according to some financial objective. We can actually say that they're rational in the sense that they optimize some private objective, which in the bottom, the equations, I won't try to go through it, but it's essentially a description of an optimal controller against some objective, even if we don't know it. So even the least rational seeming people could be argued as rational with respect to some objective we don't know. We might just not agree with their objective function. Conditioned on the actions that they take, we see state updates which are functionally deterministic. We might have an update to state that includes some states that we can't observe, and in fact those states that we can observe influence the future. And this is essentially a description of a differential equation because it can iterate over time, and because we don't control the players, maybe it's better thought of as a differential game. I'm going to talk a little bit about how I map systems out from an example on continuous organization. So some of you might have read the blog articles by Thibault on the continuous organizations and bonding curves, and I'm going to use this example to show a little bit like what we might do to construct an abstraction for one of these systems. So here we have more than just the smart contracts for the continuous organizations. We also have a representation of a secondary market of the type of a Uniswap style liquidity pool on the upper right, and we have a sort of model of the continuous organization's operations itself on the left. And what we're doing here is sort of seeing how these subsystems interrelate with each other and the appearance of some of the decision processes. So we might have traders that are herders or signal traders, or maybe they're efficient markets hypothesis traders, or some population of actors in these pink bubbles on the right is making actions in response to observations. They are acting on these mechanisms, and over here we have some purple things that represent the actual behavior of the operators of the C org itself. Interesting thing about this is that it's essentially a stock and flow diagram. Anyone who's familiar with the sort of business dynamics, system dynamics literature would see this as very similar, with the exception that I removed all the faucets and replaced them with diamonds. And the reason that they're diamonds is because these systems don't change just because. They change because someone acts on them. And in fact, the biggest challenge in these systems is often understanding how people will act and what the implications of that will be. But it doesn't start there. It starts with the shape of this system, because this is a relatively high dimensional system, but it has a lower dimensional embedding or a configuration space, something that we deal with a lot in robotics. It basically means that, yeah, there's lots of variables, but not all possible combinations of those variables can even happen. And so the shape of that space has a lot to do with what actually can or does happen. And in order to get into that, we move towards building simulations, but to build simulations, we actually need to go beyond the view of a sort of system dynamics model and more something that looks like that differential game. And so we kind of created this, I'll say, sort of scaffolding that helps us write code. That code has sort of the classical control theoretic structure where you have sort of the U layer, the inputs, and they can be random processes, they can be behavioral processes, they can be algorithmic policies. That's the top row. And we've used yellow for the things that are modeled as random processes, pink for the things that are, these are like uncontrolled controllers in the controls literature. Just means that it's behavior, someone else decides the input-output function, and we deal with it. And maybe they're optimizing themselves, maybe they're optimizing against us. We can try lots of things, but we definitely know that we don't get to pick this. And then finally, the green boxes are the things that the designers are actually choosing. As a consequence of the top row, we have state updata functions. This is basically just saying, cool, given all that stuff we didn't know, once we know that, we know exactly what happens next. And then we update our state variables, maybe compute some metrics, KPIs, or other measurables that we care about, and the whole thing starts over. In an implementation sense, this is literally a data pipeline looped on itself. Its input and output data sets are the same type. And so this is sort of the magic of how we got CAD/CAD up and running so fast, was because the lead engineer on the project is a very talented data engineer, Joshua Jodesty, and he basically figured out how to leverage the existing data science infrastructure to build these kinds of differential games as basically function compositions in data science pipelines. So we get results from things like Monte Carlo experiments. This is just like one plot. It's not going to be realistic to go into a ton of results, and this is an ongoing project. So what I really want to show is that we can start to get things happening in this sort of inexpectation kind of way. So it's five experiments, same system structure, random variables on the yellow stochastic processes that are actually martingale style. They're diverging. So these things wouldn't actually converge around a particular outcome if the system itself weren't essentially processing that information and sort of shaping it. And so we're getting a system here where, under the assumptions that we made, which were, statistical adoption curves look like S-curves, certain assumptions. The faster the adoption, the higher this might be. The deeper it is, the higher this might be. But what's interesting here is really just that the results actually kind of clump up a bit, despite the fact that there's a lot of randomness being injected on the front end. And I sort of encourage people to sort of play around with the software in the future, try things out. But what really matters here is that you need the representation of the whole system that you care about with a state space model, get it actually mapped into something that looks like a system that evolves over time, and then you can start to run simulations using a simulation framework. It doesn't really matter what simulation framework you use. The problem is that what you care about is probably stuff in this bottom row. And those things are rarely totally defined by information that lives on chain. And so these unobservable states become functionally part of the abstraction. They're estimated, and they sort of help you build out an understanding about the relation between the concepts that you care about and the things you can actually tune. So in that sense, we're going to move on a bit. Well, how do we go about approaching this? Well, we have our sort of pre-launch design of the ecosystem. We want something that will sort of enable and empower an ecosystem to behave as intended. You launch it, and then it just like totally doesn't work like that because it never works how you think it's going to work. And you have to have a means of them feeding data collected on the live system back into these models to help understand what they're really, the state they're in. And actually in the robotics literature, this is called system identification. If you have a proper differential representation of the sort of way the system evolves, even when there's a bunch of stuff that you don't know, you can actually sort of learn the stuff you don't know. It's a gray box modeling. You have a white box, this part works like this, a black box, someone doing something we don't understand, and some data about the whole system. It's sort of a sort of more advanced version of autoregression involving sort of structural dynamics under the hood. In practice with CAD-CAD, what we're doing is moving towards decision support tools for live networks as we work with our clients and help them build models during design. We are actually driving towards integrating data and learning how these systems are actually behaving, because at the end of the day, again, we know that we can't predict them. The designs are not predictions, they're not guarantees, they're simply like any other system, something that has to be launched and taken care of. And in a world where we want maybe autonomous groups of individuals to take care of systems, we need to provide visibility. And that visibility comes from this type of workflow, and I'm pretty excited about it. My friend Jeff recently wrote an article called Computeraided Governance, which is sort of exploring this idea further. And here's what it actually ends up looking like from an engineer's perspective. We do quite a bit of effort to understand the economic system, these economic conservation equations, like the first drawing we saw. We do sort of user role taxonomies to help understand what kind of actors we can reasonably expect, behavioral models, statistical models, etc. And then, of course, we have to know what the protocols and mechanisms in the system that we're working on are, from which we can synthesize these differential specifications, like the one that I showed you before, leads to computational models during design, and eventually system identification during LiveNet. And ultimately, this is all just a sort of piloting system that helps the humans design, implement, and govern these complex networks. And anyone who's really interested in how to do this, I think we should talk offline, but we're working pretty hard to put the best practices from what is essentially OR and industrial automation into play in situations where there is actually very rich data, but there is definitely stuff out of our control that isn't observable that we care about. And in the end, it's all about achieving some goals that are determined by the project and not necessarily low-level things that can be defined clearly over the low-level data. And so sort of finally, this is a slide from my cybernetics talk where I talk a little bit about the importance of this governance feedback loop. So we build these automated systems that have these interaction patterns. They represent what one can do in these systems, but then we build in these incentive systems that kind of provide automated feedback, and they drive us towards some goals. But if those goals start to come out of sync with your community or your population of this network, then there's a feedback loop through governance. And one of the things that we find is that this type of model sounds great until you realize that participation isn't good enough. Informed participation is required. It's very common knowledge even in centralized systems that the intuitive thing to do is very often the totally wrong thing to do. If you've ever played the beer game, which is common in consulting, you end up creating this thing called a bullwhip effect just by making the really so-called obvious or intuitive decision, and you get a very non-optimal outcome. And the more spatial and temporal feedback loops in a system, the more likely that doing the thing that seems obviously right isn't. And the way that we avoid that with communities governed by themselves is to make sure that they have real visibility into the most likely consequences of their decisions. And so while this might seem like a lot, I am actually saying that token engineering is engineering. Engineering is full life cycle, and full life cycle means making sure that you keep that system healthy once it's deployed. So I'm going to wrap up with this demo. So we're working on getting cloud-hosted CAD models, and we're not on the internet. Can we make it so that we're on the internet? That makes me really sad. Okay, so I'm going to do a workshop later, but the point was we actually started working on our integrations, cloud hosting, and since we have these models of the sort of data science type, we are working on getting them into places where people can integrate their models into a cloud-hosted environment and do decision support tools. The existing model here is just a demo, but it is in fact live on the internet and available for, at least with a password because we don't want to blow up the server, to try it out and play with a three-sided market model, which we're going to actually play with in the workshop at 3 o'clock. So I guess I'll show it there.
Yes, please show it there. And to remind you, at 3 o'clock, there is a workshop starting in the workshop area. The room is called Robston. It's just behind the catering area where you got your food in the lunch break. You will find it pretty easily. Just follow the red lines on the floor. Robston, it's starting at 3. And there you can take a look and also play around yourself, I guess, with CAD. And with this, thank you so much, Michael, for this talk.